so today I'm going to talk about prime numbers, right? You all know what prime numbers are. Prime numbers are numbers that have as factors 1 and the number itself, right? Like, so 3 is a prime number because it is only divisible by 1, and 3 itself. So then the prime numbers that we know are 2, 3, 5, 7, so on, 43, and then some really large prime numbers, right? And as you might intuit, prime numbers become less and less common, right? So the difference between two consecutive prime numbers is known as prime gap, right? Between 2 and 3 is 1, 3 and 5 is 2, so on, right? So that's what you call a prime gap, right? Right, and the gap keeps on increasing. The gaps between primes keep on increasing as we go down the numbers. For larger and larger numbers, prime numbers become rarer and rarer. So now the question is, are there infinitely many primes? Are there infinitely many primes, or do we reach a point where every number is a composite number being, the opposite of prime number, they have many factors, at least one other factor other than itself. So the question is, are there infinitely many primes? And the answer is yes, even though they get rarer and rarer and fewer, but and the prime gap more or less keeps on increasing. There are infinitely many primes, and there's really nice proof for this, right? And which I'll show you. It's a small proof, but it's an interesting proof. And it's actually, there are many proofs for it, but this is just one of the oldest. It goes back to 300 BC. It's a proof by Euclid. And yeah, I mean, modernized a modern version of it, right? So this is the proof, right? Suppose there are, okay, let's assume the opposite of what we're trying to prove, right? Suppose we're wrong, and suppose there are only there are a finite number of primes, right? The primes are a finite set. Primes p1, p2, so on. Maybe a large number, still finite, right? So this would be the finite set of prime numbers, and this is our assumption to start with, right? So there are finite, so say there are a finite number of primes. So what do we do? Let's construct a new number, n. So that we multiply all of this, p1 times, p2 times, so on, the product of all these primes that we know, supposedly know, or even if we don't know them, okay, suppose they're finite. I'm going to call this product pi. The product of all this plus 1, right? So I've constructed this new number. Now the question is, okay, so there are two possibilities. Either n itself is prime, in which case an n can't be any of these, right? Because we've multiplied all of them and then we've added a 1. So if n is prime, so case 1 is that n itself is prime. Okay, in which case we're wrong. It's not finite set. We keep on, we've created a new prime number. But really, usually the case is that, n is not really a prime. N is a composite number. A lot of people tend to think that this n that we've constructed is a prime number, but it's not. It looks like a prime. N is a composite number. Okay, that's the other case where n is a composite number. Right? So in this case, what happens, right? So we've created this prime, n is equal to p1 times p2 times so on, pn plus 1, so is our n. And we are saying that, okay, I'm calling this product pi, okay. And I'm saying that in the case that, which is usually the case, n is a composite. That means it is divisible by some prime number. Any composite number would be divisible by some prime, and this I'm calling it p dash, right? So n mod p would be 0, right? N is divisible by P, P divides N, right? So N mod P would give you 0. Similarly, since our set of primes are finite, this P dash has to be one of these numbers, P1, P2, one of them, right? We don't know what, but and since this would be one of these numbers, this product pi is also divisible by P dash. So P mod pi mod P is also 0, right? So in very simple words, N is divisible by N divides by P. If you divide N by P dash, you would get the remainder 0. Similarly, if you divide, which means that P divides N, and pi is also divisible by P dash, right? So if N is divisible by P dash and pi is divisible by P dash, then N minus N minus pi should also be divisible by P dash, right? It's also divisible by P dash, right? This implies that. That means N minus, so if I've taken this to this side, so N minus pi, but what is N minus pi? N minus, sorry, this N minus pi. N minus pi is actually 1, right? Because you've just effectively taken it to the side. So N minus pi is 1, and we're saying 1 is divisible by P dash, which cannot be possible because P dash is a positive integer greater than 1, obviously cannot be divisible. So N1 is not divisible by any integer, right? So we've reached a contradiction, and therefore our assumption has to be wrong. Our assumption, which was the only thing that we assumed, was that there are a finite set of primes, and our assumption is wrong, and therefore there are infinite number of primes. Okay, so we've proven by contradiction. So this is known as proof by contradiction, which is used very often by mathematicians. And this is a very simple example of proof by contradiction, right? A small example of a nice proof by contradiction. So now the question is, there's something called twin primes. Twin primes are those like 3, 2, and 3, 3 and 5. Okay, 2, 3 is one exception. Actually, 2, 3 is not really twin prime. 3, 5, 5, 7, 11, 13, right? Some of these numbers which have a prime gap of 2. Okay, so these are twin primes. Let's talk about twin primes. Okay. Now the question is, are there infinitely many twin primes? Okay, so we ask our next question. Are there infinitely, just like we proved, can we prove that there are infinitely many twin primes? And it turns out that we don't know actually. This has not been. So the conjecture is that there are infinitely many twin primes. We assume that so there is the conjecture. The conjecture is yes, but it's still not been proven. And this is one of the open problems in prime number theory, right? One of the other interesting open problems is prime number theory. There are many open problems in prime number theory, and many famous ones, right? Many of the open unsolved problems in math itself related to prime number theory. So one of the most popular ones and oldest ones is called Goldbach's conjecture. Goldbach's conjecture basically states that any even number greater than 2 can be written exactly as the sum of two primes. And interestingly, this has been tested till to the order of 10 raised to 18, 4 into 10 raised to 18. Recently, I think that happened in 2012. And up to 4 into 10 to the power 18, we've been able to show that any even number can be split into two primes, can be written as the sum of two primes. So we have not found any counterexample for it yet. At the same time, we've not been able to prove it analytically. So that is another interesting open problem. Um, Prime number theory has a lot of applications, especially when it comes to cryptography. And but yeah, mathematically they're really fun objects to play with. In one of my later videos, I'll explain how give a simple explanation for how prime numbers can be used for encryption, right? So take a look at some of the open problems in prime number theory, and let me know if you have any questions about the proof itself.